Have you ever built this perfectly optimized AI model on your laptop, only to watch it just absolutely crash and burn the second you try to deploy it? Yeah, it's frustrating, right? And super common. Welcome to this explainer. Today, we're going to synthesize some really fascinating, totally disparate technical sources to guide you through the whole messy, thrilling life cycle of an AI project. We're taking a journey from optimizing raw code locally, up into the cloud, and then finally down into the physical world of a factory floor. So if you've ever wondered how all these distinct stages of machine learning actually connect and, how to dodge the pitfalls along the way, you are in the exact right place. Let's get into it.
Okay, here's our roadmap. First up, optimizing PyTorch performance, then overcoming infrastructure bottlenecks, after that, real-world quality control, and finally, hardware and camera integration. Basically, we're shifting from the micro level of PyTorch internals all the way up to macro-level serverless cloud stuff, and then landing right in the physical world of computer vision manufacturing.
So part one, optimizing PyTorch performance, memory, and processing. Before we deploy anything, we really need to get into the weeds of our code and see how data handling might be secretly throttling your training time. It's the classic question, right? Why is your PyTorch code bottlenecking? Look, if your computation is stuck waiting on data loading, the culprit is almost always the Python Global Interpreter Lock, or the GIL. Think of the GIL like a single toll booth on a massive multi-lane highway. It doesn't matter how fast your data is moving, it all has to squeeze through that one lane, completely killing your throughput. The GIL just stops you from fully parallelizing Python code across threads, and by default, PyTorch's data loader uses a single process, so you're stuck in that traffic jam. But you can totally bypass this by tweaking the num_workers argument in your data loader. It's basically opening up extra toll booths, giving you multi-process data loading and feeding your GPU so much faster. But even with extra toll booths open, you still have to physically move that data from your CPU to your GPU. By default, it gets stuck in standard pageable memory. Your CPU has to do all this extra work just to keep track of it. But if you just toggle pin_memory to true in your data loader, you're creating a VIP expressway. This lets the data loader allocate your samples in page-locked or pinned memory. It's a ridiculously simple switch, but it creates a direct, crazy fast transfer path straight from the CPU into the GPU's VRAM. Massive time saver. Now, what happens when you scale up beyond a single GPU? You're going to face a choice: distributed data parallel or data parallel. I know it sounds a little crazy to use the word distributed when you're just on a single machine, but here is the secret. Always choose distributed data parallel. Why? Well, data parallel uses multi-threading, which means, yep, you guessed it, it slams right back into that single GIL toll booth we just talked about, bringing a ton of performance overhead. Distributed data parallel, though, it spins up a totally independent, dedicated process for each GPU. It uses multiprocessing, so it completely dodges the GIL bottleneck. All right, shifting from memory to data types, let's talk about floating point formats. When you're training neural networks, they are actually way more sensitive to the size of the exponent than the mantissa. To put it simply, think of the exponent as how wide your map is, your dynamic range, and the mantissa as how tightly you can zoom in, your precision. Neural networks care way more about having a really wide map than they do about pinpoint zooming. Notice how bfloat16 keeps the exact same 8-bit exponent size, that map width, as a standard 32-bit float, even though it trades off some of that zoom precision. That structural similarity is an absolute game changer for maintaining stability when you're crunching massive amounts of data. And that brings us to how we actually use this stuff. You don't have to agonizingly pick just one data type anymore. By using Automatic Mixed Precision, or AMP, you get essentially the ultimate free lunch in AI engineering. AMP automatically matches operations to their perfect data type for you. For instance, it'll seamlessly use float16 for linear layers and convolutions where you just need pure speed, but then it bumps up to float32 for reductions that need a high dynamic range. Plus, because of that matching exponent size we just looked at, bfloat16 is an incredibly stable drop-in replacement for float32. You get the exact same behavior for underflows, overflows, and NANDs, saving a tremendous amount of compute without micromanaging the math. Moving right along to Section 2, overcoming infrastructure bottlenecks. Let's zoom out from the local code and tackle those absolute headache-inducing infrastructure issues developers face with containers and the cloud. Look, we've all been this person, right? Staring at a terminal at 2 a.m., losing your mind to the dependency hell of environment configuration and CUDA mismatches. Take this engineer in an NVIDIA forum, desperately trying to get an OpenCV Docker image running with CUDA support on an RTX 3090 Ti. They're running custom bash scripts, trying to force it, but OpenCV just flat out refuses to talk to the GPU. It's a universal pain point that will just stop a deployment dead. But instead of fighting with these brittle, custom-built scripts, the community offered a brilliant fix. If you just pivot your Docker file to use an official NVIDIA PyTorch base image, that OpenCV and CUDA mismatch practically vanishes. Why? Because these official, hardware-optimized base images come with drivers and binaries pre-compiled by the exact same people who build the GPUs. It's a great reminder. When you're dealing with deep learning infrastructure, leveraging pre-built environments spares you from compiling nightmares and literally saves you days of work. Okay, so your app is containerized. It's bug-free. Now, cloud deployment speed is everything, especially in serverless environments where your code scales to 0 when it's idle. Which brings us to this wild number, 500 milliseconds. That is the cold start time RunPod is hitting for popular serverless endpoints like OpenAI's Whisper. Usually, spinning up a heavy model like Whisper takes tens of seconds, sometimes minutes from a cold start, which totally ruins real-time user experiences. So how are they getting sub-second cold starts? It's through an optimization layer called FlashBoot. It basically handles the entire deployment, teardown, and scale-up process in real time. And the business value here is huge. Since it tears down instantly and scales up in half a second, you aren't stuck paying for expensive, idle GPUs when traffic dips, but you also aren't making your users wait when a random traffic spike hits. It's the perfect balance of cost and performance for those really bursty AI workloads. All right, Section 3, Real-World Quality Control. We're zooming out again, taking our optimized, containerized pipelines out of the cloud and dropping them onto the physical factory floor. This academic flowchart is super cool. It shows exactly how a robust, 3-part automated quality control pipeline works for inspecting IoT devices on an assembly line. Step 1. The pipeline uses the PySbar library to extract manufacturing data right from the device's QR code. Step 2. It uses classic OpenCV template matching to check if the physical connector socket has shifted at all. And finally, the remaining images feed into a neural network. It uses ReLU to activate specific visual features and softmax to output a probability. It's essentially a hyper-vigilant digital inspector hunting for microscopic surface scratches. But here's the catch. How do you train a digital inspector when your factory hardly ever makes broken items? Industrial datasets of faulty devices are usually tiny. To get around this, researchers used image data generators to clone and manipulate synthetic training images. They artificially added zooming, rotations, and translated angles. They were basically photoshopping realistic dents onto healthy products. This clever data augmentation let the model spot microscopic defects that a tired human on a crazy fast assembly line would definitely miss. And the real-world results? Pretty incredible. The system hit a 90% accuracy score. But what you really want to look at is that false positive rate of 0.2. In factory terms, a false positive rate of 0.2 means the system is leaning just a little bit aggressive. It might occasionally flag a perfectly fine unit for a human to double-check, but it virtually guarantees a scratched unit won't slip past and end up in a customer's hands. It minimizes claim leakage and locks down absolute quality. Which brings us to Section 4, Hardware in Camera Integration, the final mile. Because you can have the best PyTorch code and the most accurate neural network on the planet, but if you can't physically get real-world image data from industrial hardware into your pipeline without it crashing, none of it matters. And right at the finish line, you can hit a massive wall with physical sensors. Just look at this poor engineer in the OpenCV forums. They were trying to pull real-time video from a highly specialized Hamamatsu CMOS high-speed microscope camera. But when they used the standard OpenCV video capture command, which, is perfectly fine for normal webcams, it completely failed. The system just couldn't even see the high-speed camera. The community chimed in with a harsh reality about industrial hardware. Standard OpenCV video capture just doesn't have the flexibility for uncommon proprietary APIs. A lot of high-end camera manufacturers don't use standard USB UVC interfaces. Standard USB is plug-and-play, like your laptop camera, but industrial gear is a whole different beast. The fix? You literally have to bypass standard commands and use the manufacturer's provided API or SDK. You capture the video directly into a raw memory buffer using their SDK, and then manually mold that buffer into an OpenCV mat object so your pipeline can finally do its job. So, we've seen how mastering an AI pipeline requires serious problem solving at every single stage. From manually penning PyTorch memory to speed up your GPU, to using optimized Docker-based images, leveraging serverless layers like FlashBoot, and finally wrestling raw memory buffers out of proprietary factory cameras. It's a complex but really thrilling life cycle. So keeping all of this in mind, what real-world bottlenecks will your next project break through? Thanks for hanging out with me for this explainer, and I'll catch you next time.